What do skyscrapers, the orbits of planets, advancements in medicine, and even the spread of ideas on social media have in common? The answer is calculus. Calculus is not just a branch of mathematics, it's the language of change, motion, and growth. In this video, we'll explore how calculus is the foundation of countless breakthroughs across the humanities, social sciences, engineering, medicine, and natural sciences. Let's dive in. Calculus is a cornerstone of science and engineering that shapes how we understand and interact with the world around us. From predicting stock market trends to designing life-saving medical devices, calculus plays a pivotal role in solving real-world problems. Calculus may not seem directly linked to the humanities, but it plays a significant role in areas like linguistics and art restoration. For example, in linguistics, calculus-based models analyze how languages evolve over time. In art, calculus is crucial in determining age and authenticity, helping restore priceless treasures by predicting material decay or optimizing preservation techniques. In the social sciences, calculus is a cornerstone of economics and sociology. Concepts like marginal utility, optimization, and predicting economic growth rely heavily on differential calculus. Sociologists use calculus to study population dynamics, analyze trends in social networks, and even measure the impact of policies and reforms on society. In economics, calculus is used to find the point of maximum profit by analyzing the rates of change of revenue and costs. For instance, companies use derivatives to determine the optimal pricing strategy to balance supply and demand. In business, calculus helps find the optimal price point and production quantity to maximize profits. By finding where the derivative of the profit function equals zero, businesses can make data-driven decisions. Businesses rely on calculus to optimize inventory management. By modeling inventory levels with differential equations, managers can calculate when and how much stock should be replenished to avoid shortages or excess inventory. Engineering would not exist without calculus. Aerospace engineers calculate optimal flight trajectories, while mechanical engineers analyze motion and energy transfer in machines, all using calculus as their guiding tool. Calculus allows engineers to analyze stress and strain in materials. By integrating stress distributions, they can identify whether a structure, such as a bridge, can handle a given load safely. Also, mechanical engineers use calculus to optimize rocket trajectories, considering factors like fuel consumption, air resistance, and gravitational forces. Signal processing in electronic engineering heavily relies on calculus. Using Fourier transforms, engineers decompose signals into their frequency components, enabling advancements in communication systems like smartphones and wireless networks. Calculus can also be found in use within civil engineering. From designing pipelines to understanding river currents, calculus models fluid dynamics. Engineers use differential equations to calculate velocity, pressure, and flow rates, ensuring efficiency and precision in infrastructure projects. In artificial intelligence, calculus powers the training of machine learning models. By calculating derivatives, algorithms like gradient descent optimize neural networks, enabling machines to learn patterns and make decisions. In medicine, calculus saves lives. It's used in medical imaging technologies like CT scans and MRIs to reconstruct images of the body. Pharmacologists use calculus to determine safe and effective drug dosages, while epidemiologists employ it to predict the spread of infectious diseases and the effectiveness of interventions. In natural sciences, calculus is the foundation of scientific discovery. In biology, it's used to model complex processes like population dynamics or enzyme reactions. Even weather prediction and climate modeling depend on solving intricate calculus equations. Newton's laws of motion and Einstein's theory of relativity, all derived from calculus. In physics, calculus models the motion of objects. By studying derivatives of position, velocity, and acceleration, scientists and engineers design everything from vehicles to spacecraft. Chemistry uses calculus to describe reaction mechanisms and energy changes. Chemists use differential equations to understand how chemical systems reach equilibrium and respond to changes. Finally, calculus is also applied in oceanography. Oceanographers use differential equations to model ocean currents. By analyzing changes in velocity and pressure, they can predict how currents move globally, allowing them to study the effects of climate change and develop response strategies. Calculus is not just for mathematicians. As we have seen, from art to various scientific fields, spanning both theoretical research and practical applications, it influences every aspect of our lives. By understanding calculus, we gain insights into how the world works and how to solve problems that shape our future. Calculus serves as a gateway to a deeper understanding of the universe. Through this lesson, let's explore how calculus profoundly impacts our lives.